Okay, so let us continue with our discussion on momentum transfer, today being the third lecture on momentum transfer. Last time, if you remember, I was talking about the momentum conservation equation in 3 dimension, taking a 3-dimensional control volume and then doing momentum balance, that is the momentum in minus momentum out in all 3 directions and equating it with the net forces. And in that context, I said that since we are talking of conservation of a vector quantity, we will have momentum conservation along the 3 directions. And I also said that, if you remember correctly, that in the momentum equations, the pressure appears as an explicit variable, and it is through the mass continuity equation that the pressure is implicitly specified. So, we have basically 3 momentum or 3 velocity components in the x, y, and z direction, and P pressure is the scalar. So, there are 4 unknowns, and in this formalism we have the mass continuity equation as well as 3 momentum conservation equations. So, as far as the number of equations are concerned, we have a well defined problem, 4 equations and 4 unknowns. So, overall mass continuity or overall mass conservation. And I chose to write last time also the equation in Cartesian coordinate system, because it is easier to write, the equations are relatively simple, but these equations are all available in standard textbooks. So, one need not do any cramming as far as these equations. Once you get yourself familiarized, and I asked you to I wrote the 2 components in the class last time, and I asked you to do the 3rd component, and I hope that all of you have really taken care to derive or arrive at the 3rd equations, given the first and the 2nd equation, and once you acknowledge that the form in which they appear as far as the convection terms as well as the unsteady term on the left hand side, and the pressure gradient, diffusion, and the body force terms on the right hand side. Now, writing this equation once more. So, for compressible, for all kinds of flows, compressible or incompressible. So, we can say that if we write down this equation, then we have, and I also suggested that we will always, before we start to write the equations, we will always specify the coordinate system, and then we will. So, that means we are talking about a coordinate system here, x, y, and z, and such that we have Vz, or the way I have written Uz as the z component of velocity, y is the y component of velocity, and x is the x component of velocity. That needs to be specified so that there is no ambiguity. And I wrote the x momentum conservation equation, and if you remember, I will put an equal to sign here, and because we are talking of a 3-dimensional equation, so I will have 1 plus 3 first order derivative terms here, then we have a pressure gradient term here, plus 3 second order derivative terms there, plus the body force term. So, that is basically the configuration in which the equation will be written. So, and if you write this equation in conservative form, the equations appears and then we say that we have the pressure gradient term, and then we have the 3 second order diffusion terms, and because it is the x momentum, so all the time I will write the partial of x with respect to x. The next term would be partial of x velocity component with respect to y, then we have partial of z component, x component with respect to z, and then we have the body force term. And in the same way, we should be able to write down. So, these are the 3 terms that I am talking about. Okay. and this, and these are the three terms that I am talking about. Three-dimensional problem, there are three convection and three diffusion terms associated with the inertial forces, associated with the viscous forces. This is the term, these are the terms which are coming because of the shearing stresses in the fluid, which I have explained to you in the context of film flow problem. So, I will have the y direction of momentum balance also. And if I write this equation, I will write down. And now you see how I manipulate. So, now I write ux uy, and because uy is the y component of motion. So, here again you will have, are you able to read it? Okay, I guess still it is still visible. Okay, so rho uy, and then we have uy uz, and then you have the same pressure gradient term, but with respect to y, and then you have, instead of these three terms are going to be repeated, but instead of ux you are going to write uy 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 along the x, y and z direction, and then we will get the same. So, I will write mu d uy dy. This is the first term, sorry, this is x, and then we have the second term, then we have the third term, and then we have the components of the gravity force. Of course, the gravity force terms will vanish. And I can also write, these equations are sometimes in literature you will see they are written as equations of motions along the x direction, equation of motion along the y direction, equation of motion along the z direction. So, if I do it, equation of motion along z direction, I am writing two different things, but as I explained to you, x momentum equation or equation of motion along the x direction is same. I am writing it so that it gets noted by you, equation of motion along z direction. And then we will have the same term. This is again, I repeat, we are having I am writing this equation in the conservative form. I am not taking out rho, mu, etc., which are otherwise constant in most of the problems that we deal, out of the brackets. So, this is the conservative form, and then I can write down, say, ux uz, ux uy uz, and then I will have uz uz, and then pressure gradient along the z direction, plus the second order derivatives, first with respect to, then with respect to y, and then with respect to z. And then I have rho. And in terms of the coordinate system chosen, you must note here that the components of the gravity along the z direction is going to be minus g, because 9.8, because the z axis is directed in this particular fashion. Now, I have written this equation because I want to explain that, how many boundary conditions one should be able to write this, and that needs to be understood, because often you will get the equations and you have to write the boundary conditions. So, you must understand it is not enough for us just to say that we have 4 different variables here, okay, uy and uz and p, and we have 4 equations, and that is why the statement of the problem is complete. No, as far as equations are concerned, we will say that yes, it suffices that we have 4 equations and 4 unknowns, but that these are differential equations, and we all know that when you integrate differential equations, we have constants of integration. So, therefore, we will need some boundary conditions and initial conditions. So, we have a first order derivative with respect to time, and then we have second order derivatives as well as the first order derivatives, and at the first sight it may look to you horrendously complex that how many boundary conditions I should be able to write for this, but there is a very easy way of writing it, and that I will show you that how to write the number of the boundary conditions. And then once we know that how many boundary conditions are needed, we should be able to write down the boundary conditions explicitly, understanding the nature of the boundaries that a given problem involves. So, let us make this table. So, first column we will write dependent variables. The dependent variables in this case are 4. Now, we will write down independent variable. And this independent variable we have, as you know, and time. What we are now going to write below this line is the order of the highest derivative. That is what we are going to list. It is actually a 12 class exercise, but I am doing it so that you have been out of touch with maths for a long time. Metallurgists at least do not do much maths beyond their first or second year. So, that is why I am doing this exercise. So, now if you look at ux, what I want, that along x I want the order of the highest derivative. Now, ux, if you look at the first equation, along x direction I have a first order derivative, and along x direction I have a second order derivative. So, along x the order of the derivative is going to be 2. Similarly, if you look at ux is the dependent variable, along y you will see that this is 2, this is again 2, and this is. In this case, I would like you to note that space, because these are space coordinates. So, as I have explained, they are two-way coordinates. So, therefore, we have two boundary conditions each, but there will be a class of problems where maybe this term will not, we will do the simplifications and see that this term may be 0, this term may be non-existent, and then the highest order of derivative along x would be 1, and I would write 1. But for a complete 3-dimensional problem where no simplification is applied, this represents. Similarly, if you go to y, we will also find out for y also it is the same thing. The second order derivative, along the x direction we have here the order of derivative along x is 1, the order of the derivative along x is 2. So, therefore, we have 2. And then with respect to time, it is first order derivative. So, same thing if you do and if you sum them up 0, 7, 0, 7, 0, 7 and 3. This represents the total number of boundary conditions, initial and boundary conditions. With respect to t, I say these are all initial conditions. So, 7 plus 7 plus 7, 21. So, on velocity components I require 21 conditions, and on pressure I require 3. So, altogether 24 boundary conditions will be necessary, initial plus boundary conditions will be necessary to define the problem completely. So, we will write down the mass continuity equation, we will write down the momentum conservation equation, and then now we have to write down what are the 24 boundary conditions. You must remember that for a 3-dimensional metallurgical engineering problem, we will be solving unsteady problem, we will be solving this. If you go to an aerospace engineering person, or if you go to a person who is doing cloud physics modeling and solving the momentum conservation equations, he will also apply the same governing equations. The governing equations will not change. It is the geometry of the system as well as the boundary condition which will change from one engineering field to another engineering field, or one problem to another problem, and that will eventually make the solution, because the solution depends on the boundary conditions in the system geometry. So, even though the governing equations are going to be identical, The momentum conservation equations used by mechanical engineers are not different from the momentum conservation equations that we apply. They are the essentially same equations, but ours would be different. There would be an internal combustion engine, or aerospace engineering would be using an aircraft, okay, in order to solve these equations. So, their domains are going to be different, and so are the boundary conditions, and as a result of which they will get one kind of solution, we will get another kind of solution specific to the systems that we identify. Now, having said that 24 boundary conditions, what it essentially means, you can now understand that if you have a three-dimensional control volume, for example, I write it like this. So, you can imagine that there are already 6 faces. This is one such face I have identified, and this face is essentially, this is the face. So, there are 6 faces. On each face I will require information, because this constitutes the boundary of the system. Okay? It is through these boundaries that the system is separated from the universe or the surrounding. So, therefore, there are one such surface here, another surface here, and if you look at the three-dimensional control volume, there are 6 such surfaces. On each surfaces I have 3 velocity components. So, 3 multiplied by 6 becomes 18. This is the whole lot here. Okay? So, if you see here, 2 plus 2 plus 2, 6, and 6 multiplied by 3, 18. So, that is what physically it implies, that on each of these faces I will require information on the 3 velocity component. But that I have time as an independent variable, also I will have to have the initial condition. If I do not know the initial condition, if I do not know the boundary conditions, I will not be able to solve the problem. So, these are to be supplied. Okay? And there is a way of writing. The initial conditions will be written, for example, t is equal to 0, and the boundary conditions are going to be all written at t greater than 0. Okay? So, I say this is applicable to IC, initial condition, and this is applicable to boundary conditions. An initial condition, for example, could be that all the fluid contents inside this control volume could be taken as stationary. So, there is no ux, there is no uy, there is no uz, and all this control volume means what? So, if I have this side as A, okay, this side as B, and this side as C, this is the height of the control volume, okay, then I can say that, and in terms of my coordinate systems chosen, I can say for all x varying 0 to A, for all y varying between 0 and B, for all z varying between 0 and C, which essentially encompasses the domain of the control volume. So, within these limits at time t is equal to 0, if the fluid is stagnant, I will say ux, uy, uz, they are all equal to 0. So, that is how the initial conditions are prescribed. Boundary conditions, as I have indicated, they are going to be, because these are the physical boundary, they will be applied on planes or the surfaces. And so, this represents maybe at x is equal to 0, and this plane on the other hand may represent at x is equal to A. So, on 2 different planes I will have to apply the boundary conditions along x direction, and 2 on y direction and 2 on z direction, and respectively. So, before I write down explicitly that what are the boundary conditions, having understood that there are 24 conditions which are going to be necessary. So, I would say as far as the initial condition goes, I will write like this. Initial condition is that t is equal to 0, okay, for all values of x, for all values of y, for all values of z, which I have indicated here, ux, uy. It need not be 0. If there is a velocity, my requirement is that you must be knowing that velocity to get that what would be the flow in the system at time t greater than 0. That is the task basically. So, this condition, initial condition, must be given, and that is represented. Now, let us look at that how are the boundary conditions written. Now, in the context of the film flow problem, we have seen, and I have also told you, that we can have a solid wall is one type of boundary. We have also seen that this solid wall could be either moving or stationary. That is what two types of solid wall we have seen. I have also explained to you in the context of discussing symmetry that symmetry could be another type of boundaries. Okay? I can exploit if there is a symmetry in the problem. I need not do the whole of the film. In that case, I would say, for example, a film flow between two parallel plates, where the two parallel plates are moving in the same direction with equal speed or velocity. In that case, I can apply a symmetry boundary condition or a symmetry line through the center, which I will draw like this. If this is the plate that I am talking about, this is the plate, another plate I am talking about, and there exists a line of symmetry, and this is, both of them are being pulled downwards, and as I say that every time I will write down that what is the axis, and this represents therefore the cast any speed c. So, there exists a line. So, this line I would say as the symmetry. So, this is also possible. I am not saying that there is a symmetry, there will be a symmetry in every problem, but we may encounter a symmetry in case of our systems also. And in our, we also can see that we can have a free surface, particularly in problems of our interest. So, these are basically the boundaries that we are going to see in our cases, because most of the time in steel making systems, okay, what we are going to see, or steel making or metallurgical systems, what we are going to see, that we will have, for example, a vessel. Any vessel, you can take a converter, for example. Our vessels are all bounded by a wall, and then we have, so this is a solid wall, this is a solid refractory wall, this is a solid refractory wall, these are all solid refractory wall, and so therefore, the fluid is bounded by from three sides, as you see on the two-dimensional picture, solid wall, and it has a free surface here, and which actually is an interface. Okay? This interface need not be horizontal, it is very complex, but if we assume that the interface is horizontal, okay, in that case the interface is drawn not by a solid line, but we will draw like this. That represents. So, this phase is the liquid contained in the vessel, and this phase is the ambient, I would say, and this is truly an interface. So, most of our systems are going to be bounded by, particularly in the context of fluid flow problems. Okay? And in this case, as you can see, that we can have actually a line of symmetry, because it is a frustum of a cone in the upper part which is symmetrical, this is the lower part is also a truncated cylinder. So, therefore, I can say that this is solid wall, this is solid wall, and if I have a symmetry line, then the symmetry can be exploited here also. So, I can use 1 free surface, 2 solid wall, 3 solid wall, and 4 which is the line of symmetry. So, these 4 boundary in the context of 2 dimension. Okay? And you can see that if you think of this as a 3-dimensional picture, then at the front also you have a solid wall, at the back also you have a solid wall. So, this problem therefore will have in its 3-dimensional entire complete form, it will be bounded by, the geometry is going to be bounded by 4 solid walls, one at the front, other at the back, and one is here third, the other is fourth, one symmetry plane which is this, and a free surface. So, these are the kinds of boundaries that we are going to really see in the context of metallurgical problems. Now, as far as the solid wall goes, at solid wall we always apply no slip boundary conditions, but I would like to say that many of our systems, this is an idealization. That is, we say if the solid wall is stationary, then the fluid in contact with the stationary wall is also stationary. If the solid wall is moving down with a certain speed, then the fluid in contact with the solid wall is also moving down with some speed. This may not work all the time in our cases, particularly because most of our vessels are refractory lined, and our vessels, because of weightability reasons, contain a lot of graphites, and as a result of which, since there is an incomplete weighting, so therefore the hypothesis of a no-slip boundary condition may not really apply in our system in a rigorous sense. But we will continue to apply as far as the classroom exercise goes, that if the wall is moving with a certain velocity, the fluid will also be taken to be moving with the same velocity, and if the wall is stationary, the fluid. So, characteristically we will say at wall no-slip boundary conditions are going to be. At symmetry, typically normal to the symmetry, normal component of the flow, which is, if you have 3 components of the velocity, you must understand one is acting in this direction, horizontal, the other is acting in this direction, and the third one is acting in this direction. But if this is a fixed boundary, in that case we understand that the fixed boundary means that the normal to the interface velocity must be equal to 0. And at this free surface, typically what is done is, since this phase is metal phase is having a greater density and viscosity than the ambient, which is typically air. So, we say that this metal, the circulation in the metal is not really causing huge motion in the system. That means there is no shear which is transferred across the interface from the fluid to the gas phase, which essentially tells us that the gradient of parallel to free surface components, parallel to free surface components of velocity are 0, normal to free surface, I write capital Fs, free surface, normal to free surface component is 0. Same thing is applied also on the symmetry axis, for example, because nothing can cross the symmetry axis, and then there is we will have a symmetry, because symmetry requires that either there is going to be a minima or there is going to be a maxima. So, a similar type of boundary conditions are applied. So, free surface boundary conditions and symmetry boundary conditions are more or less same. They will apply on one component which will be 0, and the remaining 2 components, the gradient of this are going to be really is equal to 0. So, these are the 3 different kinds of, or if you take the variations of moving and stationary, 4 kinds of boundary conditions that basically we are going to get into the system. Now, for example, if you consider now flow between 2 parallel plates, a very simple kind of a flow. Suppose this is a parallel plate and this is a parallel plate. And the parallel plate, the way I have drawn it, suppose it extends infinite along the z direction. So, I would say that this is taken as, again, and the depth direction, which is perpendicular to the board, is actually 0. So, basically I have shown a 2-dimensional scenario here. So, and suppose we have basically an entry region, and we also have basically an outflow region. So, in problems, in most of our problems, we will not get this kind of a scenario, but this is called an outflow basically. So, at the outflow, we can also consider that outflow is a physical boundary. Okay? But as I said, that because we have a fixed amount of metal contained in the vessel, in this kind of a system, we will not get an outflow. But you imagine, for example, outflow, if you know that, for example, metallurgical vessels which are used for example, to hold molten metal and then transfer. For example, ladles you will find in all metallurgical industries, either it is in zinc industry, aluminum industry, or in steel industry. Ladles have basically they are cylindrical vessels, but they have a hole also at the bottom. Okay? So therefore, what happens is the molten metal from the ladle is drained into another vessel through the hole which is located at the bottom. So basically, if you have an exit here, this will be treated as an outflow. You can have here, for example, this is a free surface, here there is ambient here, this is the ladle, and then if I am draining the molten metal, of course, the free surface will be going down because molten metal will be taken out from the ladle itself. But this basically represents a flow outflow through which the fluid really is transferred from one vessel to the other vessel. This is a very common. We will solve some problems when we proceed further and take up the tutorials and then find out that what would be the complete emptying time taken to empty a ladle, for example, holding 150 tons or 200 tons of the system. Now, if you look at this scenario, so it's a two-dimensional problem. Basically, we have an inflow here and we have an outflow here. So, on the fifth, I can also say, typically at the inflow, we can measure the parameters. Okay? So, the inflow boundary conditions are always known to us. For example, water may be flowing through this, I can have a flow meter attached here, or gas may be flowing through this, I can have a gas flow meter attached, and I will be able to know at what rate gas is entering into the system. I may or may not know the outflow depending on the configuration of the scenario. I have shown here only one outflow, there could be another outflow here also. And there the area of the outflow can be different. So, these are complexities in the system, but essentially there is not much difference. So, you can say that the inflow boundary conditions are known, okay, and the outflow boundary conditions basically are an assumed bound. In the outflow, typically what happens is flow is normally assumed to be parallel, that is where there is no backflow because the fluid does not really enter into the system. And since it is one-dimensional flow, so one-dimensional flow is essentially assumed at the outflow, and that one-dimensional flow means we will retain the first order derivative and drop the second order derivative. Everywhere the second order derivatives on moment velocity components are going to be applicable, but come the outflow, at the outflow boundary, we will assume that the flow is predominantly unidimensional, which essentially means that space is now behaving like a one-dimensional coordinate. Okay? You can go from left to right, but you really cannot come back. There is no flow reversal in the system. This is an idealization because we have constructed the boundary here, and that's why that is the price we are going to pay, okay, in order to make that idealization. And we will say that if the flow is one-dimensional, it is going out in this way and nothing is coming in, then the diffusion term is absent. So, the second order term will be dropped, and therefore, at the outflow boundary, the fluid flow equation will behave as if. So, basically, outflow must satisfy the mass continuity, that whatever mass is coming in at steady state, the mass will be going out from the system. That constraint it has to fulfill, and then by assuming that the flow is one-dimensional, the outflow, which we call as a standard outflow boundary condition, okay, that at the outflow, diffusion will be set to be equal to 0. You need not always do that. There are advanced schemes which are available also to handle the outflow boundary, but in this, if you wrongly choose the outflow boundary, for example, I can tell you that choice of the outflow boundary is very, very important. Suppose you take a problem where you have a sudden expansion geometry. The flow comes here and the flow goes something like this. And then we have a reversal of flow here, and then a reversal of flow here, and ultimately, so this is the domain. So now you can see that the flow is basically, if you apply the outflow boundary outflow in this domain here, you say that my outflow is located here, sir. I would say it is the correct location of the outflow because the flow is leaving the domain. But if someone does calculation by saying that the outflow is placed here, I would say no, this is not outflow because there is a reversal of flow taking place. So the choice of the outflow boundary is very, very critical where fluid may not be necessarily going into the domain and it should be unidimensionally flowing, exiting from the domain of interest. So, in this particular case therefore, in the context of this two-dimensional scenario where the z direction is assumed to be infinite, I will say that look, either I can do this part when I will have a solid wall, an inflow, an outflow and a symmetry axis, assuming that both these walls have identical condition, either they are both stationary or they are both moving in the same direction with the same speed. Or alternatively, I can say that I can do over the whole and then I can say that look, my system is bounded by one wall, two wall, one inlet, other inlet, and that is what a two-dimensional problem really is. The third dimension does not come into the picture. So, therefore, I have to specify ux, uy, ux, uy on this domain and ux, uy on this domain, ux, uy on this domain, ux, uy on this domain. Okay? So, therefore, on this domain I will say that ux is equal to uy is equal to 0, ux uy is equal to 0. In this, if the flow is parallel, okay, or I can say that there is a cross-sectional average velocity. So, I can say that look, ux is given and uy, which essentially is saying that the fluid is entering with a horizontal component of velocity. It does not have a velocity which is in the y direction itself. And then the outflow is, I would say, I will apply the standard outflow boundary condition, which essentially means that dux dx is equal to 0 and duy dy is equal to 0. There is no gradient of x and y along the x direction. So, whatever is the value here immediately adjacent, the same is the value at the interface. That was the meaning of the boundary. So, the boundary conditions are specified. So, this is the inlet condition. If I have to write, then I would say inlet has a. So, if this is x is equal to 0, so I would say, and if this is a steady state problem, I would say the inlet actually is what? Inlet is at x is equal to 0 for all values of y. Y is equal to 0, so suppose y is equal to, I will say h, in which h represents, and this represents, I am not invoking any symmetry conditions. Okay? So, at x is equal to 0, x is equal to 0 for all values of y. That means, on this line segment, I am saying that ux, there is a normal component of the flow is given, which I have measured with the flow meter, and uy is equal to 0. Similarly, if I say this solid wall, I would say that I will write what is this value? This value is at y is equal to h. That wall is y is equal to h, and this represents, if this is L, then for all values of x, I do not know, I am writing it a little up, so I will just write it here. So, the boundary condition can be written as for y is equal to h, that represents this particular wall for all values of x. So, x is this, and then I will say I need boundary condition on both ux and ui, and they are going to be all 0 because this wall is taken to be equal to 0. I do not think that I should spoon feed you any further. So, you should be now able to understand, and write boundary conditions exactly the same way, so that do not just write that ux uy is equal to 0 at inlet. No, you have to mathematically express, because you are writing a mathematical framework. Okay? So, write down the continuity equation, write down the momentum balance equations in their exact form, and then you write down the boundary conditions, draw the system geometry, show what is the span of the domain along x, y and z direction, show the coordinate axis, everything you label down, and then you write down all these things very systematically. That will show that your understanding of the problem is very, very clear. So, for every problem therefore, the equations can be written. As I said that this is a two-dimensional problem. So, I can start with the three-dimensional equations which are available to me in the textbooks, and then I can say, look, I am dealing with a two-dimensional problem, so I do not have to do anything with the third component of the velocity. So, I can drop a momentum conservation equation, and I can drop corresponding term from the equation of continuity or mass conservation equation, and very quickly I can establish the governing equations for this particular problem, rather than trying to set up a two-dimensional control volume and trying to do momentum in minus momentum out and is equal to net forces which are acting onto the system. That will be too time consuming and it is not justified. So our approach would be, in general, we will take the governing equation in its complete form and then simplify it to our scenario or adapt it to our scenario, write down the boundary conditions and then attempt to solve these equations. Now, in this context, I would also like to say that each of these terms, these three equations that I have written here, they are termed the Navier Stokes equations. Navier Stokes equations. The momentum conservation equations, okay, that I have represented in 3 dimension, they are basically, this R is silent, so it is called Navier Stokes equation. Now, these equations, the equations that I have written, okay, if you look at the term, for example, last term, what was the last term, for example? The last term essentially is rho g. That was the 3 equations I have written, rho g x, rho g y, rho g z. That is the path. What is the dimension of this? You know that m into g is force. So this is force per unit volume. That's what. That's what is. So therefore, in the momentum equation, okay, so this is kg per meter cube, and then we have mass into acceleration. So this term is the force term and force divided by volume, that's what. So therefore, the unsteady state term, the first order derivative term, the second order derivative term, the pressure gradient term, all these terms have the dimension of force per unit volume, because the equation has to be dimensionally homogeneous. Okay? Now, therefore, if you imagine that if I divide all these terms, for example, by rho g, if you consider the first equation, x momentum conservation equation, now you should be able to, even though the equations are not on the board, I would like you to visualize the equations. That the moment I say x momentum balance equation, you should immediately realize that I am talking about one unsteady term, 3 convection terms is equal to the pressure gradient term plus 3 diffusion term and the gravity force term. That should immediately appear in your mind. Okay? So in your mental eyes, you should be able to see that, even though the equations are not there on the blackboard. So imagine now, if I divide all the terms in the momentum balance equation by the rho gx, then the last term will be 1, because the last term was rho gx. I have divided all the term. So similarly, all terms, when you divide, what does that indicate? The last term is 1, which does not have any dimension. So therefore, applying the principle of dimensional homogeneity, I can say now all the terms in the equations have become dimensionless. Okay? So therefore, the Navier Stokes equation, which I have represented in dimensional form, can also be represented in a non-dimensional form. And if you look at the Navier Stokes equation, so therefore each term, what you are doing, we are dividing by force, because it is force per unit volume, and you are dividing by another term, okay, which is also force per unit volume. So essentially it becomes dimensional, non-dimensional term. Now, if you look at the Navier Stokes equation, we have 4 different kinds of forces we have considered: inertial, gravitational, pressure, and viscous. These are the forces that we have considered. The first order derivative terms, ux into ux, those are the inertial terms associated with the fluid motion. Gravitational term, the rho gx. Pressure term, that's what is the pressure gradient term, and the viscous force term, that is the term associated with the viscosity of the fluid, the second order derivative term. So you can imagine now, therefore, if I have divided by gravitational, so I can get one term as inertial by gravitational, the other term as gravitational by gravitational, pressure by gravitational, viscous by gravitational. So what I am going to get, because I have considered 4 such forces in the development of the equation. This is not the end of the world, as I have indicated, that if I have a electromotive force acting in the system, I would act the Lorentz force also. If there are surface tension forces, there could be surface tension force appearing here as an additional force. There could be a buoyancy force acting on the system because I have injected a gas bubble into the system. Okay? But we have represented the Navier Stokes equation in a very simple form and assume that there are only 4 forces, and we assume that if any additional force is assumed to be acting on the fluid element, we should be able to conveniently add and say that the 5th force is going to be surface tension force, 6th could be Lorentz force, 7th could be buoyancy force, and so on and so forth. But for the time being, let us not complicate the discussion. So, therefore, when you use 4 terms and express the equation in the dimensionless form, you will find out that we are going to generate 3 dimensionless force ratios. So, we will have a term, 3 terms characteristically. They are going to be force ratios, and the 4th term is going to be unity, which is going to be also dimensionless because all other terms are dimensionless. So, in that context, the force ratios are basically what we call as dimensionless numbers or dimensionless groups. For example, if you have inertial by viscous force, I could do the same thing. Viscous, if I divide by the viscous, then I will get viscous by viscous 1, pressure by viscous 1, and gravitational by viscous 1, inertial by viscous 1. The moment I get inertial by viscous, this is the way, inertial force by viscous force. This is called the Reynolds number of the flow. Similarly, if I say that inertial by gravitational, I am not writing the full form, we will say that this is the Froude number or FR. Don't pronounce it as Froude number, it is called Froude number, okay? And this is Reynolds number. So, this is one ratio that we have obtained. This is the second ratio that we have obtained, and I must be having the third ratio also, and the third ratio basically is called the pressure by inertia, pressure force by inertial force, and this is called the Eulers number. So, therefore, the Navier Stokes equation that I have written can be represented in a non-dimensional form as Eulers number, Reynolds number, that basically represents. This represents Reynolds number, as you see, inertial to the viscous force. I can say that the viscous, what is the expression of this? The expression of this is Reynolds number expression, you all know, all of you, will let rho u into L by mu. This obviously does not have the force term, actually it becomes, then it becomes truly, if you multiply numerator and denominator by UL, then you get rho u square L square divided by then. This becomes the viscous force. If you now take the unit of mu, unit of u, unit of L, then you will find out this has come out to be in the unit of dyne or Newton. Similarly, if you take the unit of rho u square u as well as L and substitute it here, this will also come out to be in dyne or Newton, meaning that you are essentially getting a dimensionless number. We also call sometimes dimensionless group. So, in fluid flow, the dimensionless groups which are important are Eulers number, Reynolds number, Froude number. We also have, for example, other numbers. A Weber number can come where we can have the surface tension forces to inertial forces and so on and so forth. But these are in the present context, we did not go and extend the discussion because this is not a very advanced level course as far as the dimensional discussions are dimensional groups and we will discuss all these things in the context of heat and mass transfer actually in more greater detail, and then I will will explain further. Now, in the context of the fluid flow equations, I just want to mention that, okay, let me complete the discussion. So, this is the inertial to gravitational, and this is basically called u square GL. That is the way it is written, in which I say that what is this u? U is a characteristic velocity in the system. The moment I will apply the known inlet velocity, I will say my Reynolds number is based on the inlet velocity. If I put L as the inlet dimension, then also I will say, and L represents basically a characteristic length of the system. Okay? For example, for circular cross-section pipe, the characteristic length through the flow, okay, is not that streamwise direction, but it is rather the diameter of the cylindrical pipe. Similarly, for a spherical object, you have the diameter of the sphere taken as the characteristic length. But suppose you imagine that you have a system like this, and then you say, sir, what is going to be, because there are different dimensions, length and breadths are not all identical in this particular say. Okay? So, in such a system, if the flow is taking place, what should be the characteristic length? Should it be this direction or should it be this direction? And in that context, there is the terminology again, you must have heard about it. We call it as a equivalent diameter or hydraulic radius. So, hydraulic radius is the characteristic length, and that essentially the definition is 4 into weighted cross section by weighted perimeter. I do not have to explain this. You must understand that what is the weighted cross section and what is the weighted perimeter. So, and then this is cross section means cross sectional area, weighted cross sectional area. So, this is an area dimension, this is a length scale. So, you get dimensional also it is constant. So, you will either get it in meter or you will get it in centimeter depending on in which unit you have really expressed the cross sectional area as well as the weighted perimeter. So, for cylinder as well as sphere it is straightforward. For cubical sections there is only one length scale, but if you have rectangular section or an irregular section you can find out a hydraulic radius and apply that hydraulic radius in the estimation of the characteristic length itself. Pressure force by inertial area, this is basically written in the context of Navier Stokes equation as pressure force. So, if I multiply it by L square, then becomes pressure force, and then I also multiply it by L square, and then this becomes pressure force by inertial force. So, that is the meaning. Or I say basically from this one can also write that Euler's number is a function of Reynolds number and Outflow number. That is also another way of writing this equation. So, the Navier Stokes equation can be dimensional in non-dimensional form expressed like this, or it can be expressed in the following way. And therefore, one can write that Euler number is written on the left hand side because it contains the variable pressure field which is dictated by the flow motion. Okay? So, I have written it like this is a dependent variable and these are the independent variables, that is the form in which it is basically written. Now, if you look at, so therefore, basically one can say that this comes out to be n, if you do a dimensional analysis, one can show this through dimensional analysis by applying Rayleigh's method of indices, and this pre-exponent as well as the exponents m and n are to be determined for a flow system by conducting experimental trials. And we will discuss this extensively in the context of heat transfer and mass transfer, where particularly convective heat transfer and mass transfer, where which will derive the corresponding heat transfer correlations and so on. In this context, the last point that I want to make before I disperse is that there is a theorem which we call as a Buckingham Pi theorem, which is very important. And this Buckingham Pi theorem is very important for us to know that how many dimensionless groups a system can really express itself. So, the Pi theorem essentially tells us that if we have n number of total variables, total means dependent plus independent variables, and m represents, and suppose beta represents the number of fundamental units involved. In that case, the number of the pi group a relationship is going to be expressed is dictated by this. So, what is n? Sum of the dependent and independent variable. Now, suppose as you can see u, the velocity, is a function of characteristic length, okay? Then we have viscosity, then we have density, then we have acceleration due to gravity, then we have pressure. This is what it turns out if you imagine, look at the Navier Stokes equation. So, the velocity depends on the characteristic length because x, y, z dependents are there. It depends on mu, second order term contains mu. It depends on rho because all the first order terms contains rho. It depends on the g, acceleration due to gravity, which is in the last term, and this depends on p. If you look at this, then how many total number of variables are there? This is the dependent variable, these are the independent variables, 1, 2, 3, 4, 5 and 6. So, I will put 6 here. What are the fundamental units involved? This is meters per second, this is meter, this is kg meter per second, this is kg per meter cube, this is meter square per second, and this is Newton per meter square. So, if you find out all 3 major dimensionless numbers like kg, there is a length scale, mass scale, length scale and time scale are involved. So, beta is equal to 3. So, therefore, 3 minus 3, and that tells us that 3 dimensionless groups will be necessary, and you see that I have written 3 dimensionless groups in order to express the Navier Stokes equation. So, we will continue in the tomorrow's lecture and show you further that what are the limiting cases and how can you simplify these equations and solve to extract some meaningful velocity profile and so on and so forth. Okay.